Hi, everyone. Welcome to my Nurex workshop talk on meta-learning, on the curse of low-task diversity, on the failure of transfer learning to outperform MAML and their empirical equivalents. Work done by me, Brando Miranda, and my fabulous team, Patrick Yu, Yusheng Wang, and Sammy Koyeyo. Work done at University of Illinois, Urbana-Champaign, and Stanford University. Introduction: few-shot learning and meta-learning. Meta-learning is important because it's one of the fields that studies how to build flexible general systems that aim to transfer to many tasks, like humans do maybe. We focus on few-shot learning, where a task is given a few concepts like ships and fishes. We try to, from these few shots, to generalize to recognizing ships and fishes. Then we transfer, and that's the ultimate goal, where we have a new task with unseen concepts like dogs and road signs, and we hope to, with few shots, to generalize to detect them. So the problem setting, what problem is my work trying to solve? Is our work trying to solve? When is transfer learning better than meta learning? That's the problem. So recent work shows that fine-tuning the final layer can beat sophisticated meta learning algorithms like MAML. It's been suggested that maybe we need to rethink meta learning and few-shot learning, but how exactly? We propose to rethink as follows: to take a data-centric perspective by studying quantitative properties of benchmarks and datasets that we use. In addition, by doing systematic and fair comparisons of transfer learning and meta-learning methods. In this work, we specifically compare fine-tuning the final layer with a fixed feature extractor pre-trained on using union supervised learning. So just using all the tasks at once or all the labels. And MAML, model agnostic meta-learning, that includes a gradient descent pass in its feed-forward pass. Summary of the problem setting and related work. Is transfer learning better than meta learning? So in the past, we have tables like this, where there is multiple backbones, multiple models, multiple methods with different training regimes, and who knows until how they were trained to convergence compared to other transfer learning methods. Too many variables are changing, too hard to draw conclusions. Instead, we propose to do a fair systematic comparison where we fix the architecture, we fix the optimizers, and all models are trained in convergence. In addition, we want a data-centric perspective, i.e., we want to contextualize our results and previous work with concrete dataset properties and statistics, hopefully statistics that are related to inductive biases for meta-learning and transfer. Proposal. So this is the proposal: to rethink meta-learning and few-shot learning by doing a fair comparison of meta-learning and transfer learning, using the same architecture, the same optimizer, and training to convergence. To showcase this, we use MAML and fine-tuning the final layer using USL, contextualizing any comparisons by computing concrete dataset metrics that might be related to meta-learning and transfer, especially trying to concretely specify inductive biases for meta-learning. In particular, we propose to compute the diversity of a few-shot learning benchmark, which we will explore, which we will describe in a bit. So conclusions up front first. Under a fair comparison and a data-centric perspective, fine-tuning the final layer using a pre-trained backbone with USL does not outperform MAML in meta-test accuracy. And it's statistically significant. Benchmarks that we used have low diversity, according to our novel diversity metric. All comparisons were done fairly with the same architecture, same optimizers, trained to convergence. And yes, but what is diversity and why might it matter? So task one is, say that we have a task sampled from natural images with ships and fishes. And similarly, we have a task two from the same benchmark that generates natural images with dogs and shoes. This has a low task distance because all images and tasks are sampled from natural images. So we want to define that this, or hypothesize that this is a low diversity regime by defining diversity as a low average task difference. Similarly, in a high diversity setting, we have images of, for example, these omniglot digits, handwritten digits, and natural images. And then there's a higher task distance here. So we assume this might be a high diversity setting, and this would happen because there would be a high average task difference. But why might diversity matter for meta learning? So the goal of meta learning and transfer learning is to learn to transfer. Therefore, for one to transfer, there must be some task difference. Otherwise, there's no reason to adapt or to learn to adapt, or no reason to transfer. The proposed inductive bias that we're proposing is future learning benchmarks is that the transfer is needed when there's a task difference, and therefore there's that diversity. So diversity is correlated with, is defined as having a high task difference. So say that we have a task 1 and there is a low diversity. And this is how our benchmarks so far have been used. For example, mini ImageNet are a bunch of images from natural images, and which begs the question: are we even evaluating our methods on the right benchmarks? Are they really being trained to transfer? We argue many past benchmarks were created like that, and that future and current benchmarks are not exactly like this, but instead focus on combinatorial measures, like just increasing the number of data points and hoping something happens magically. In the high diversity regime, however, we have a more mindful approach for data creation, where we have digits and natural images combined. And that's what future work should focus on, being more like option 2 and creating more mindful benchmark creations. In this talk, we will focus on the low task diversity. So formally, let's define the diversity coefficient. We propose the diversity coefficient should measure the average distance between tasks, or an approximation to distances between probability distributions. So we have a task 1 and a task 2. There's some task difference, and we define diversity to be the average task distance. Formally, we propose a diversity coefficient of a benchmark B to be the average distance between embeddings of tasks. So diversity div of benchmark B is equal to the expected value of task tau 1, tau 2, sample for a common benchmark, and we compute the average embedding distance of tau 1, tau 2 using a fixed probe network. For task embeddings, we use previous work, task2vec, which uses the diagonal of the Fisher information matrix. This embedding correlates empirically and theoretically with remaining metric spaces of probability distributions. For details, refer to their paper and our own paper. Methodology. So the methodology is that we want to clarify and contextualize current observations, and transfer learning is better than meta learning. We will compare fine-tuning the final layer versus MAML by comparing their meta test accuracy with confidence intervals. Do comparison fairly by using the same architecture, same optimizer, and training models through convergence, and contextualize our findings by computing the diversity coefficient of the benchmarks or data sets. So now we're going to go to the experimental results. Experiment 1, computing the low diversity. So recall our conclusions. Under fair comparison and a low data diversity, fine-tuning the final layer using USL doesn't outperform MAML. All datasets used have low diversity coefficient according to our new measure. So this is what we want to show in the following table. So we have 4 different probe networks, a ResNet 18 and a ResNet 34, with different weights, PT and RAND, which are pre-trained on ImageNet and just random weights. For these probe networks, we compute the diversity on mini ImageNet, MI, and the diversity on CFAR-FS. So the first row shows that when using a pre-trained network using mini ImageNet, trained on ImageNet, the diversity of mini ImageNet is 0.1, and for CFAR-FS is 0.1. What follows is that we do similar experiments to compute the diversity using the other 3 networks and show that they are all around the same value, 0.1 or below, with confidence intervals that are quite good. Why do we consider this low diversity? Since, just looking at the table, it might be random numbers in a table. So we want to say that first, the maximum task-to-vec distance is 1.0 due to the cosine distance of task embeddings. In practice, when ground truth diversity is available, i.e. when the true distance between distributions are available because we know that the actual distributions, the maximum task-to-vec diversity we observed was 0.55. And this is going to be shown in the figure on the right. On the figure on the right, the x-axis show the Hellinger diversity because we use the Hellinger distance between for our synthetic data set. The y-axis, we use task-to-vec diversity, which is the one we are suggesting to use in practice for real data sets. We show that when the maximum diversity is present for the Hellinger distance, which is 1.0, that the task-to-vec distance gets a maximum value of 0.55. And the correlation between these two is quite high, which is 0.99, meaning that task-to-vec diversity is a pretty good representation of the ground truth diversity. Experiment 2, fine-tuning doesn't outperform MAML. So recall our conclusions and settings again. Fair comparison, low dataset diversity, fine-tuning USL does not outperform MAML, and this is the slide where we show this. So what we want to show is compare the meta test accuracy of each method. So the y-axis is the meta test accuracy, and the x-axis is the datasets and the pro networks that we use. So focus on the first bar graph, where we have a 5CNN and mini ImageNet. So the green line is the green bar is a USL, i.e. only fine-tuning the final layer. And the green and the orange one is using MAML 5 and MAML 10. So in particular, we noted that all of the errors are around 60. And in particular, USL, just fine-tuning the final layer, is slightly lower. This pattern remains for all of the other experiments. Using a ResNet 12 on mini ImageNet, again, USL is below the other two bar graphs. For CFARFS, that happens again. And for CFARFS with ResNet 12, that happens again. So experiments 3. Fair systematic comparison. We want to show that we did a fair systematic comparison by sampling 2 learning curves from all of our experiments. So this is our learning curves. We see how we trained on supervised learning, and the model converged into one of the lowest losses that you can get using cross entropy, and similarly with MAML. So this is true for all of our learning curves. Experiment 4. Does this similarity hold as model size changes for a small 5-layer convolutional net? This is a particularly interesting slide, because the hypothesis is that large models might be better meta learners inspired by GPT-3. However, perhaps small models benefit from meta learning, and the diversity doesn't explain our observations. Our results suggest no, MAML cannot actually outperform fine-tuning even for small models, meaning that the low diversity is likely a bigger factor explaining our observations, i.e. the task difference is small, so any adaptation method is sort of similar, is the intuition. So on the x-axis, we have the filter size that we use for a 5CNN. So we use a filter size of 4, 8, 16, 32, and then we compare USL and MAML 5. I only fine-tuning the final layer from a pre-trained supervised learning network, and compare a model using MAML 5 for adaptation trained on MAML 5. So we see that the losses are quite similar, and the confidence intervals often intersect. And this also holds even if you change the adaptation. Even when you try to adapt it with more steps, the intersection between the two curves still remains. So again, this curve is the same, except that MAML 10 is being used for adaptation. So the conclusions for this slide is that the low diversity is a bigger explaining factor, explaining our observations, and it's not about and that MAML didn't help even when the model was smaller. So these are the summary of our conclusions. Under a fair comparison, and in the low diversity regime, fine-tuning the final layer does not outperform MAML, and it's statistically significant, even for small models. We hope this inspires future work to compute quantitative metrics of datasets that might correlate with meta-learning, and move beyond only increasing the size of the dataset. Maybe we should increase the diversity too, or other related inductive biases that might induce meta-learning. Thank you for your attention. Any questions? You can contact me at brando9@stanford.edu.